There are two main uses for logarithmic differentiation. We've seen the first use, which is when we have a function that's got a whole bunch of factors in the numerator and denominator that would cause us to have to use the product and the quotient rule. The second example where logarithmic differentiation is really helpful is when the variable is found both in the exponent and the base of the same expression. And I'm going to show you an example right now. Let's differentiate y equals x to the square root of x power. Now, none of the rules of derivatives that we've learned before are going to apply here. We can't use the power rule because that would be x to a numerical power. We can't use the rules with exponential functions because that would be a number for the base to a power with x in it. Basically, this falls outside the realm of the different types of functions that we've looked at so far. And this is our other situation where we can take the natural log of both sides and end up with something where we can use implicit differentiation. So let's start by taking the natural log of both sides. That's going to be ln of y equals ln of x to the square root of x power. But remember that when we have a power inside a logarithm, we can bring it out front as a factor. So this is going to be ln of y equals the square root of x times ln of x. And now we've got something that we can differentiate. We just use the product rule here. So let's take the derivative of both sides with respect to x. So we've got d over dx of ln of y equals d over dx of the square root of x times ln of x. On the left-hand side, when we differentiate ln of y, that's going to be 1 over y, but remember, times y prime, because y is a function of x. We've got to use the chain rule there. On the right-hand side, we're going to have to use the product rule. We've got the derivative of the first times the second. Well, the derivative of root x is 1 over 2 root x times that second factor, ln of x, plus the derivative of the second, which is 1 over x, times the first, which is root x. All right. Now, I want to simplify the right-hand side just a little bit. We can write this as ln of x over 2 root x plus root x over x. Now, at this point, to get the y prime alone, we can multiply both sides by y. So this is going to give us y prime equals y times all of that, ln of x over 2 root x plus root x over x. And then we want everything in terms of x, so we can replace y with x to the root x. And that gives us y prime equals x to the root x times ln of x over 2 root x plus root x over x. This is a fine final answer. This is okay. But there is actually a cheeky way that we can combine the two fractions in parentheses as one. If we look at that rightmost bit, the square root of x over x, remember that x is the same thing as the square root of x times the square root of x. And so we actually can cancel out a factor of root x in the top and bottom, leaving us with 1 over root x. But we know the other denominator is 2 root x, so we can also multiply the top and bottom by 2 if we want, giving us 2 over 2 root x. And so we can take that, and now that we have a common denominator between that first term and that second term, we can actually write it as one fraction, which is a little bit nicer. That's going to be ln of x plus 2, adding those numerators together, over 2 root x. It might be, sorry, that was y prime, not y. It might be a little bit nicer to write it like this, because if the next step is looking to see where the tangent line has slope 0, then we would need to see when the derivative is equal to 0. And so we would basically need to see when this numerator is equal to 0. So having it factored is a little bit nicer. Having it combined into one fraction is a little bit nicer. But really, you might not notice that. And for me, the important thing is to recognize that we have found a way to differentiate this function that none of the other rules we previously had learned would allow us to differentiate. So even if this might not be the simplest answer in the end, it is nice that we are able to use this method to differentiate things that have variables in the base and the exponent.